Now we are going to continue to work with the previous imagery data set, and that involves classifying the fruit images. And now we are going to work with the convolutional neural networks. And you can read in all of these packages, import torch, numpy as np, and so on. I'm going to carry out the same steps as before, loading the data set and transform into tensors, and nothing's changed. So I'm not going to discuss these data in any more detail. In this chunk, as you know, we split the data set into training and testing. So we have 6517 for training and these many for testing. We have 15 classes to classify. And these are the kind of images we are working with. Now we'll try to implement a convolutional neural network, and this is the architecture of my neural network. So I have the input layer, it is an RGB image, therefore we have 3, and the pixel size is 100 by 100, and we are going to feed this into a convolutional layer of these particular dimensions, and then we feed it through a ReLU. Then we go through the maximum pooling layer, another convolutional layer, and these are the dimensions: maximum pooling, more convolution, maximum pooling, and ultimately the softmax layer. And then we obtain the 15 classes, or the image classifier, which will help classify the 15 images. And this is how the architecture of the convolutional neural network has been put together. So as you know, conv layer, just to explain, conv layer is the convolutional layer, ReLU is the activation function, and we have it at every stage. Max pool is the pooling layer, FC stands for fully connected layer, and the softmax is the activation function of the output layer. And usually in CNN problems, we inevitably use softmax as the activation function. And we can use this formula to check the size of the layer by the given parameters. As you know, this is the input size, 3 channels and RGB, 100 by 100 pixels. We have the first convolutional layer, which expects 3 input channels, and it will co-involve 6 filters of sizes 3 into 9 into 9. The padding is set to 0 and stride is to 1. So the output size becomes this. So basically this is how we come up with the size of 92 by 92. Then we have the first maximum pooling layer, and we use a 2 by 2 kernel and a stride set to 2. So basically with this we get this particular size, which you can see over here. Then we have the second convolutional layer, which is going to expect 6 input channels and will involve 8 filters. So we have 8 filters, and each of size 6 into 7 into 7, and this is how we come up with 40, the maximum second max pooling layer. And basically if you just go over this is how we came up with the different layer sizes. And finally we reach the second fully connected layer, and output of the first fully connected layer is connected to another connected layer with 300 nodes, and it's right here, and we use the ReLU activation function. And finally the softmax, and we have the softmax activation function for the output layer, and the fully connected layer uses softmax, and it's made up of 10 nodes, and 1 for each category in the fruit data set. So we get 15 nodes in the output layer. And for your convenience, this particular architecture is available here as well. Now we can import torch nn not functional as f, import torch nn as nn, class model nn module. Now this is how we are going to define the convolutional neural network in the language of Pytorch. So super init self conv, we put in 3 channels, output is going to be 6 channels. And then we have the 6 channels. Output is our 8 channels. And then we have the linear layer 8 into 8, 300, FC2, 300, because these are the node sizes and the class numbers. In the forward function, we define the activation function, which is the ReLU activation function, and then the maximum pooling layer, which uses a 2x2 filter like so. And finally, we return f.log softmax, and this is for the output layer. And here x.view, we just carry out the flattening operation by using the -1. So we can print the model, and you can see conv layer 3 into 6, kernel size 9 by 9. So basically whatever I described before, this is how we put this together in a convolutional neural network using Pytorch syntax. And then we have import torch optimizer. We use the cross entropy loss, and we use the stochastic gradient descent optimizer Adam, and this is our learning rate. Now we are ready to train the model, and even with a convolutional neural network, we are going to have forward propagation, loss computation, back propagation. Loss arrays, we have 30 epochs, and we are going to iterate all of them. And now we are going to carry out forward propagation, implement model on the data, compute the loss, and we compare the output model with the target variables using the cross entropy function. With loss.backward, we do the backward propagation, weight optimization, and basically these are the losses at the different epochs. And this is the training loss like so. And then this is model testing. We again do the same stuff as we did before. So we are going to use the test loader, and again use variable data, variable target, feed it into the variables data and target, output, model output, and then essentially we have the actual labels and the predicted labels like so. And we can compute the accuracy, and we get 100% accuracy. So we have exactly the same steps as we did in the previous artificial neural networks and deep neural networks. All of it is same. The only difference is how we define the convolutional neural network over here.